Hello and welcome to lesson 32. Today we are looking at compound interest. So last class you were introduced to interest and rates of change, specifically with simple interest and compound interest. And today we're only looking at compound interest and what that can look like, and also how to do calculations and word problems involving compound interest. And specifically, we want to find the present and future value, which means if you have a certain amount of money right now and you invested, after a certain amount of time, how much money are you going to have, which will be the future value, or vice versa, if you want a specific amount saved up after a specific time, how much do you need to invest right now in order for the interest to compound and become that future value that you do expect. So before we get started with our example, some key vocabulary to know. So future value, as mentioned, is the amount of the money at a future date after interest is applied. And remember, these problems can be both for saving as well as loans. If you're also borrowing money with compound interest, that can also be the amount that will be due later on. So in the formulas, future values use is represented using FV or the variable A, commonly A. And present value could be denoted PV or P. And again, that's the initial principal or the current money that you have right now before any interest is applied. And so, again, if we're thinking of saving money for a specific amount, it's the amount that we need to invest at the present time for the money to be saved up to the goal that we have. Next, we have interest per period. So this one is a little bit different now from the rate of interest. So last lesson we saw rate of interest, which could be 5%, 10%, 2%. But now interest per period applies for compound interest because the rate is only for the year. But with compound interest, that money or the interest is being applied on a different perhaps period. And that's actually called the compounding period. So for example, interest could be compounded biweekly, it could be biannually, it could be monthly, and depending on that, the interest per that period is going to change. So take, for example, a 10% rate, and if it is being compounded biannually, which means twice every year, then each compounding period, which will be 6 months, that 10% is going to be divided by two. So you get 5% after 6 months and then another 5% after the next 6 months. And consider, for example, if you're getting the 5% after 6 months, you're of course getting part of the interest then. So when you get that 5% in the next 6 months, you've already accumulated some interest. So actually, you might be earning a little bit more because you have a greater value mid-year. That amount could also be, for example, monthly. And if it's 10% and then it's monthly, then each month it's 10 divided by 2, and that's the interest per period for that month. So just as our definition, the interest applied each compounding period. And again, that could be yearly, semi-annually, monthly, and I'll show you some more at the end of this lesson. So given an annual rate R, and the annual rate also is usually denoted R, whereas the interest per period is I. And if there is the compounding periods, then we have to consider how many times per year. So again, if it's monthly, and here would be 12. So R would be divided by 12. If it's weekly, it would be 52. Or if it's quarterly, it would be divided by 4. And again, we write this as a decimal, not the percentage. So you do have to convert by dividing by 100. Then we have the number of periods. So again, if we're thinking of 1 year and it's monthly, that's 12. But now consider if you're saving for 3 years, we do have to account for the number of years as well. So it would be 3 times 12, 36 would be your number of periods. So your interest is being compounded 36 times over 3 years, as compared to if it was just 1 year. And the compounding period is how often interest is added. And just don't confuse compounding period with number of periods. Compounding period is how much or how frequently your interest is compounded yearly, whereas the number of periods is over a total amount of time that you're saving or borrowing that amount of money. How many times is that interest applied? And of course, more frequent compounding yields more interest and future value. Again, consider because you're accumulating interest each time the interest is applied. So then you're earning more in consequent compounding periods. Now, the formula for compound interest, and this again, we work with it with exponential functions, but now we're just putting the financial context here. So, future value, and these two are the same formula. I just wanted to show you that it could be given to you as PV and FV, or it could be given as A and P. And so your future value is going to be your present value, and then 1 plus I, remember I is the interest per period, and uh, to the power of n, which is the number of periods. Now, present value, it's the same formula, just rearranged. So it's more if we're solving for PV or P, then we are dividing. So your future value would be divided by 1 plus the interest rate per period and to the power of the number of periods, or again with the P and A representation. And so through this lesson, we're going to see different examples where we're going to be using these formulas to calculate either future value or present value. So let's get started with our first example. $1,000 is invested at $6 per annum, compounded quarterly for 3 years. What is the future value or the amount at the end? So one thing here, the 6% per annum, or you might see 6% per A. This just means annually. And here we are told this is compounded quarterly, so that's our compounding period and over 3 years. So first, especially when we're starting with these financial questions, I always suggest write out what you're given. So all the values that are given to you and use the variables that were just presented in the vocabulary. So the present value P is $1,000. The rate of change, again, annually 6%, so R is 0.06. This is divided by 100, but it's compounded quarterly. So we do need to calculate I. And if it's compounded quarterly, that's every 3 months, then that's 4 times per year. So N is 4 here, the compounding period per the year. And so I is going to be R divided by N. And so our interest rate per quarter is 0.015. So each quarter, when the investment is earning interest, it earns at a rate of 1.5% or 0.015. You could have also done 6% divided by 4 to get 1.5% and then convert to a decimal, but either way, it's the same answer. So now, just so you visualize it a little bit better, after the first quarter, so of course you have the $1,000, and that's what that one there is really telling us, right? And now you've earned 1.5% interest on the $1,000, which means you earned $15 interest and you already had $1,000. So after 1 quarter, you have $1,015. Now, after the second quarter, the interest that's being accumulated because it's compound interest and not simple interest is on the $1,015. Remember, simple interest, if we calculated that $15, then that's the amount that was being applied every quarter. So the second quarter, you'd also earn $15 and so on and so forth, and you'd just be earning $15 each time. Whereas here, it's going to be a little bit different. So here, after the second quarter, we're earning that 1.5 interest on $1,015. So then we have that $1,015 times 1.015. And again, this $1,015 coming back to here was really $1,000 times 1.015, which is right here. And then we're also multiplying by another 1.015. And so if we combine these two using exponents, we have 1.015 to the power of 2, which also makes sense because it's 2 quarters that have passed. And so now, after 2 quarters, we have $1,030 and 23 cents. So, as I was saying, with the simple interest, you would only get another $15 the second quarter, which means you would have gotten $1,000 and $1,030. Whereas here we get that 23 cents as well. And right now it may not seem like a lot, but usually you're investing for a long period of time. So over time, it's actually going to accumulate. And I do suggest at the end of this, you do try this with simple interest to see how much you would have earned with simpler interest and make a comparison to the end figure to see the difference that it actually makes. So now, because we're considering after 3 years, that n is going to be applied by multiplied by 3. So we had 4 quarters a year, but then 3 years, so 12 quarters in total. So the $1,000 is being compounded 12 quarters, so 12 times at a rate of 1.5%, 0.015 quarterly. So using our formula, the future value, or again, remember this is just A, is going to be equal to 1,000 times 1.015 to the power of 12. And here we get $1,195.62. So after 3 years, the investment will be $1,195.62. So I'll actually do the comparison for simple interest for you. So again, remember if it's simple interest, we already calculated that we would be getting $15 per quarter, but that $15, which was calculated based on the principal value, is not going to change. So you would have $15 and compounded 12 times. This is going to give us $180. And I'll hold on to that, or actually, we'll leave that. So you would have had $1,000 plus the 180, and so your total would have been $1,180 at the end. And so comparing to the amount that we actually earned, that's a $15.62 difference. So you can see after 3 years that clearly made a difference. And again, this might not seem like a lot for like to consider $15 for 3 years, but you might also be investing a lot of money. So if this was $10,000 instead of $1,000, that would have been a $150 difference, and maybe even more if you're investing more. So over time, of course, compounding period is going to accumulate more interest for us. And the opposite could also be said when you are borrowing money, and it is compounded, the interest is compounded, or it is compound interest, then you're also earning more interest that you have to pay later on as well. So, bit of a double-edged sword. So, now the question here, how much interest was earned in 3 years? Pretty simple. We would just calculate the amount that we have. What did we start with? We had $1,000 we started with, so we earned $195.62 as our interest. So, sometimes you will be asked what was the total amount at the end of the 3 years, in which case you have to consider your principal amount. Sometimes you might be asked how much interest was earned, in which you need to deduct that principal amount. So make sure you also know what you're being asked in order to write your final answer. And don't forget your concluding sentences, regardless of what you're asked, you do need to finalize your thoughts. Just as a sentence, you repeat pretty much the question and input your answer that you found. Now let's go on to our second example. So Charles wants to have $2,000 saved up in 5 years. He finds an account paying 4% per annum, compounded annually. And how much should he invest today to the nearest dollar? So this is now an example where we have the future value and we want to know the present value. And so again, make sure you write down what you're given. So here the present value, PV or P, is what we're trying to solve. And the value we are given is the future value, or FV or A, which is $2,000. Now, because they count the rate that's given to us is annually, we need to calculate per compounding period, but actually here it is compounded annually. So then really the rate of interest is the same as the interest per compounding period, because the compounding period is for the whole year or compounded annually. So I is going to be equal to R, and it was 4%, so 0.04. And it's 5 years, so T or N in this case would be 5. And so now we're using the formula, but again, we're solving for P. And also, when it comes to the formula, you don't really need to remember both formulas, right? Because one is derived from the other. So as long as you remember the formula for future value equals present value times 1 plus the interest, so 1 plus I to the power of n, then really you can derive this from that very easily. So here, present value is going to be the future value divided by that 1 plus I to the power of n or t. And so we had $2,000, and it's going to be divided by 1.04 to the power of 5, which is going to give us $1,643.85. And because we were told to, or we were asked the value to the nearest dollar, then we just round up to 164 or $1,644. So to have $2,000 saved up in 5 years with that interest rate, he should invest $1,644 today. And now, what if he wanted to save $5,000? How much should he invest today? So again, we're using the formula, but we're just changing the 2,000 to 5,000 now. And so we can see, and again, it's the same 5 years. We're not changing the period of time. We're just saying instead of $2,000, what if he needs $5,000? So that means today he needs to invest $4,109.63, or rounding up, $4,110. So clearly that's a big difference for the amount that he wants, but of course he's going to be saving up more if he's investing more as well. And another follow-up could be, how about if he wanted to save that $2,000 in 2 years instead of the 5 years? So now we're using the same formula, but the one from here, because A is going to be 2,000 again, but now T or N is going to be equal to 2. So here, the change is that A is 5,000. And here the change is that N or T is equal to 2, because it's 2 years. So now using the formula, and again, rate of change, everything else is the same. So 1 plus 0.04 to the power of 2. And now we get $1,849.11. So that makes logical sense to us as well. If he wants to save up in a short amount of time, he needs to invest more. And rounding up to the nearest dollar, we have $1,850 today in order to have $2,000 saved up in 2 years. And again, make sure you are paying attention to what each question is asking you with regards to the period of time, the rate, and how much investment you have either now or how much you want in the future. And I think this is our last example. So consider a principal rate or principal amount of $10,000 and a rate of 10%. So we're asked to compare how much the final amount will be if the account is compounded yearly, semi-annually, monthly, and weekly. And we're asked which is the better option. So one thing you'll notice here is that we're not told the amount of time. So this is a hypothetical, so we're not actually saving up for a specific amount of years. So for comparison, as long as the timeline that you choose is the same for all of them, then your answer will be the same. So of course, the easiest option here is to just pick over 1 year, because of course, if after 1 year, one option is giving you more money, then after 2 years, it's also going to give you more money. So we would say here, this is all after 1 year. You can also, just to challenge yourself, try to change instead of, so T or N is equal to 1. You can try to change that to 2 or 3, but you have to keep that the same for all of the options. So you should see that you still get the same answer. So the first option is if it's compounded yearly. So that means T or N is equal to 1. We're only compounding once. And I is going to be the same as the rate, and it's 10%, so 0.1. So then the future value, or A, is going to be 10,000 times 1 plus 0.1, and just once to the power of 1 because it's 1 year, and we get $11,000. Now, if it's semi-annually, that means every 6 months, then T or N is going to be 2, and the interest per period is going to be that rate divided by the number of periods, which in this case is 2. So 0.1 divided by 2 is going to give us 0.05, or 5%. Then the future value is going to be 10,000 times 1 plus 0.05 squared because it's twice over that year. So then we get $11,000 and $11,025. And right away, I can already see this is giving me more value than the yearly option. So already I'm seeing a pattern, but we're going to keep going to confirm that. Now, option three is monthly. So when compounded monthly, that means N or T is 12, so 12 months a year. And the interest per period over the year is going to be R divided by N, in this case 0.1 divided by 12. And this is approximately 0.083. And with your rates, I suggest keeping four decimal places. You won't get anything that's small, like significantly smaller than that. But of course, you can see if we're sticking to two decimal places, this is going to give you 0.01, which is not very accurate. So four decimal places generally gives you an accurate response, or you can just use the fraction form, especially if you're using online calculators, or if your calculator has the fraction option, I highly recommend you stick with the fraction option when you are inputting your formula here. So then the future value for monthly is going to be the $10,000 plus, as you see here, I kept the fraction, 1 plus 0.1 divided by 12, and 12 as the exponent because it's 12 times over the year. And again, here, this is $11,047.13. And again, this is greater than this value and even greater than here. So my pattern is continuing. Option four is weekly. So in a year, we have 52 weeks. So T or N is going to be 52. Your interest, which is going to be R divided by N, is going to be 0.1 divided by 52, which, keeping four decimal places, I get 0.0019. So now the future value here is going to be $10,000 times 1 plus 0.1 divided by 52, and to the power of 52, because we have 52 weeks in the year. And we have $11,050.65. And this is our winner now. It has the most value after the 1 year. And so the pattern continued. And of course, we can now make a generalization, which also would answer this question here. So how do you explain the difference between the future value of the different compounding periods? So of course, we can say when the interest is compounded more frequently, then that means our future value is going to be greater. And similar to the explanation I gave you at the beginning of this lesson, consider that you're accumulating interest more frequently. So for example, in the weekly case, every week you're earning money. So then the amount that you're earning is on top of that interest as well. So it adds up over time. And that was, oh, and just one last thing I'll show you here. Just like a little cheat sheet. Hopefully after you practice a few times, especially once you are familiar with these terms, you should be able to do this on your own. But just to start you out for now, annually is going to be once per year, semi-annually is 2 times per year, quarterly is 4 times per year, monthly is 12 times, weekly 52 times, and you might have a daily option, 365. Generally, we don't go for leap years, we just count general time. Or they could even give you another option as well. They'll say like 5 times per year on 5 different dates, and then you would have to account for that as well. And so when you're calculating I, which is the interest per period, you are just dividing by all of these values here. So pretty much how often you're compounding. And N is going to be the number of years. So, or the T that I used, I just wanted to differentiate T and N for you. So N could be the compounding periods per year, whereas T will be based on the number of years as well. So if you have 3 years semi-annually, then T is going to be 6. And N, which is also going to affect I, is going to be 2 because correction, N is in this case the number of years. So if it's 3 years semi-annually, then this would be 3 times 2, 6. So your exponent will be 6. Or if it's daily over 3 years, you would do 3 times 365, and that will be your exponent value there. So again, I highly suggest that you try on your own to problem solve and come to these conclusions yourself and not just use the table as like a reference, but of course it is here for you to use as well. That is the end of our lesson for compounding or compound interest. And you have some practice problems here. There's also some extra questions on this website if you want to get just more familiarized with compound interest. And check Google Classroom for any other additional tasks posted. And I will see you all in our next class.